Dynamics of simple harmonic motion. In physics, a period t is the time for one cycle. So obviously the best SI unit for t is abbreviated with an S, seconds. The frequency f is the number of cycles per second and is often measured in the unit hertz, abbreviated Hz. The equation relating t to f is t is 1 over f. Those are reciprocals. In uniform circular motion or simple harmonic motion, the variable omega is called the angular frequency and has the unit of radians per second. In the sinusoidal curves we've been working with, one cycle of uniform circular motion or simple harmonic motion is equivalent to 2 pi radians of angular displacement. Thus, if we focus on period, what's omega? Well, omega is radians per second. One cycle's worth of displacement, one cycle's amount of time, radians per second. And since frequency and period are inverses of each other, another expression is omega is 2 pi times the frequency. All right, moving on. The figure shows a mass in simple harmonic motion. We've got a mass on a spring here. The mass is given, the spring constant is given. It's oscillating back and forth on a frictionless surface between a positive value of displacement of positive A and a negative value, negative A. Draw a free body diagram of the mass when it is at some distance x between x equals 0 and x equals positive A. The mass we need to imagine is somewhere about where my pen is. And what would a free body diagram look like right there? There's the mass right there. mg down, normal force up. Those would be numerically equal to each other, wouldn't they? And if we've displaced this mass to the right, then there's going to be an elastic force equal to k times x directed that way. That's its magnitude, certainly, and it points to the left. Hooke's law is F elastic is equal to negative k times x. The elastic force is one type of restoring force, which is any force whose magnitude is directly proportional to the object's displacement. And you can see that in Hooke's law that the force and the displacement are linearly connected by some constant, the spring constant. The negative sign in Hooke's law indicates that the elastic force is directed always opposite to x. In the example that we considered here at the top of the page, if the mass is displaced to the right, that is, if x is positive, then the force is going to be trying to pull it back to the left in the opposite direction. Similarly, if the mass is displaced to the left, the force in the spring is going to be acting to the right to try and put it back into equilibrium. So the force and the displacement are always opposite each other. Write an x direction Newton's second law equation, then substitute Hooke's law into it, then solve for the mass's acceleration. If you recall, that free body diagram looked like this, and then we had that magnitude was k times x directed that way. The net force, Newton's second law, is equal to the mass times the acceleration. The net force on this is, I'm just going to write it as k times x for a second, and that should equal the mass times the acceleration. Now, here's the thing. When the displacement is to the left, then the acceleration is going to be in the direction of the net force, which is to the right. What we need to do here is we need to put a negative sign in there somewhere. If this thing is displacing to the right, then x is positive. Well, that means that the force is going to be directed to the left, which means the acceleration will be directed to the left, which is negative. So there has to be a negative sign in here somewhere. Doesn't matter where. And then let's solve it for the mass's acceleration. So this acceleration is going to be the opposite of Did I do that right? Put that down there. Kx over m. All right. Into that expression, let's put the appropriate simple harmonic motion equations. Now, this harkens back to an earlier video, so hunt that down if you need to. But in simple harmonic motion, the acceleration looked like this. Opposite, the amplitude times the angular frequency squared times the cosine of omega t plus phi. That's the left side. And on the right, let me pull that negative k and that m out. And what was x equal to? X was a times the cosine of omega t plus phi. Now we need to solve this for omega. And that looks kind of ugly. However, there is a lot that cancels here. Look at this. The negative sign goes away. Let me scribble that out. The amplitude goes away. Scribble that out. The cosine monster goes away on each side. What are we left with? Omega square root of k over m. Ooh, that was nice, wasn't it? Look at that. Let's use that now to determine the angular frequency and the period for each system. So we just established that the angular frequency is the square root of k over m. And what about the period? Didn't we say earlier, let me do a little bit of scribble work here. Didn't we say that the angular frequency was 2 pi divided by the period? That was early in this video. And so once we know what the angular frequency is, then we can find the period because it'll be equal to 2 pi divided by omega. So I think if we use those equations here, we're going to be good. All right, can we do this in our head? K is 32. Let's look at the units. Newtons per meter and kilograms. Those look good. So if this is 32 and this is 2, that's 16. Square root of 16. So omega, in this case, is going to be 4. What's the unit for angular frequency? Radians per second. And then if we put a 4 right in here, that's going to be pi over 2. So that's going to be, you could leave it as pi over 2 if you wanted. Pi over 2 seconds, that would be fine. Or if you want to change it into a decimal, it's about 1.57 seconds. But we need to put the seconds unit on there. All right, how about the next one? What if we put a 24 in the numerator? Oh, no, 6 in the numerator, 24 in the denominator. That's square root of 0.25, which is a half, isn't it? 0.5. You check me on that. Radians per second. All right, then if we put that under here, put 0.5 in here, that's essentially 4 times pi, which is about 12.6 maybe, 12.6 seconds. If you want to write it as 4 pi, that would be okay as well, 4 pi seconds. All right, let's do one more. K is in the numerator and the m is in the denominator, so you know what, I will write this out just so I don't make a mistake. 4,900 over 100 square rooted, 49, 7 radians per second. And if we put a 7 under there, that's going to be 2/7 pi seconds. All right, whatever that comes out to be. That'll be a hair less than 1, maybe. About 0.9 seconds, something like that. All right, let's combine part F with an equation we used in part A and derive a hopefully recognizable equation for the period of a mass spring system. Actually, I think we have both of these equations in here, don't we? That omega is the square root of k over m, but it's also 2 pi over t. If we solve that for period, what does that give us? Put that over there. 2 pi times the square root of m over k. You check and make sure I've done that correctly. I don't know if you have seen that previously in physics, but in our first year physics class, we cover the period of a mass spring system. Look at that. That's where that equation comes from. That's pretty neat.